Hi guys, welcome back to my channel. Let's talk about weak acids and bases today. So according to the AAMC content PDF, there are 3 things you need to know about weak acids and bases. So the first one is dissociation of weak acids and bases with or without added salt. And number 2 is hydrolysis of salts of weak acids and bases. And lastly is the calculation of pH of solutions of salts of weak acids and bases. And you're like, oh, whoa, wait a second, what is this, right? This is not making any sense, right? You're like, oh, I remember from my Genchem class is that weak acids and bases, they're weaker than the strong ones, so they don't fully dissociation in the solution. Or you may also remember weak acids, how the pKa and Ka is different than the stronger ones, right? Okay, so I agree with you that this list is not straightforward, okay? It doesn't make sense the first time I look at it. I was like, what is the salt of weak acid? What is the salt of weak base, right? Okay, so today we're gonna break it all down for you and then really gonna look at this weak acid and the base topic from the MCAT perspective, okay? Let's dive into this. So first, we're gonna talk about the dissociation of weak acids and bases without added salt, okay? Let's not add any salt yet. So before we even dive into that, let's take a look at a few weak acids and bases that you may see on MCAT, okay? So the first weak acid is acetic acid here. So you see this has a carboxylic acid group and then it's attached to the CH3, right? Okay, and then the second one is the benzoic acid, and then still I have the carboxylic acid, but this time it's connected to the benzene ring, okay? And then the third one is a formic acid, and then still my carboxylic acid connected to the hydrogen, okay? And move on, let's see the hydroformic acid, okay? So I know fluorine is the most electronegative atom, but trust me, HF is a weak acid, okay? All right, and then hydrocyanic acid, HCl, hydrogen sulfide, H2S, and then the famous water, H2O, right? And water is not just a weak acid, it's also a weak base, right? And the other weak bases are ammonia, NH3, amine, and this means that the tertiary structure amine has stronger basicity than the secondary one, than the primary one, but they're all weak bases. And then the pyridine, and then the ammonium hydroxide, okay? So one thing I want to point out before we move on to the dissociation is that every weak acid has its conjugate base, right? I mean, every acid, even the stronger ones, right? So the conjugate base is really you take that proton off so that you get O minus, okay? All right. And then the conjugate acid of those weak bases on the opposite side is really adding a proton. Also, it goes from NH3 to NH4 plus, okay? All right. Okay, so now let's talk about the dissociation. Okay, so you may have seen the equation or reaction, something like HA goes to A minus and H plus, right? So I've seen this too, right, in my Gen class on internet, and I found this really annoying, okay? This is confusing, especially if you're new to this, you know, because I want to write everything out for you, okay? So how do we write everything out? Let's just take one of our weak acids, let's say acetic acid. So when acetic acid, CH3COOH, when it dissociates, it really dissociates in where? In water, right? So this is the aqueous form plus water, okay? H2O, which is the liquid form. And then it would dissociate into CH3COO minus and plus H3O plus, okay? I mean COO minus and then H3O plus, okay? So as you can see, as an acid, what does an acid do, right? No matter how weak it is, as an acid, you give away proton, you donate proton, right? So that you see that this hydrogen is gone, right? We don't have the hydrogen here, the oxygen becomes negative. And then who gets the proton that the acetic acid give away? It's the water, right? Water here is a base. So water really grab the proton, so it goes from H2O to H3O with the positive sign, right? Okay, so this is the dissociation of my weak acid. And then compared to the strong acid, the difference is that the strong acid would fully dissociate, meaning like HCl, right? HCl plus water. And then you will have a H plus and then Cl minus, right? And then really this is just this, right? And then this. Okay, so really all the HCl will be used up, right? All you have in your solution is your products, right? Whereas my weak acid, if I have like 2 moles of the acetic acid, maybe 50% of these, only 1 mole would dissociate into 1 mole of the each product, okay? All right, I hope that makes sense. And then let's do the dissociation of the weak acid, okay? So we haven't added any salt yet, okay? This is all happening without salt, okay? So you may also have seen the reaction like B goes to BH plus and then OH minus, right? This is also pretty annoying because it's what does it mean, right? So now let's write it out, okay? Let's take ammonia, okay? NH3, that is our base, and still it's in the water that it dissociates into NH4 plus because base would grab a proton from what? From where? From water, right? Remember Ochem mechanism, I always draw something like that, base grabs a proton, the arrow always goes from the base to something, it grabs the proton from something else. So I always remember the base would receive a proton, whereas the acid would give away a proton, right? Okay, so now water loses a proton, right? Since the base grabbed a proton, so the water goes from H2O to HO, so we denote it as OH minus, okay? Okay, perfect. So these are the reactions, right? The weak base and the weak acid, and then weak base, just like weak acid, it doesn't fully dissociate. You still have some reactants in your solution, okay? All right. Now let's add the salt, okay? See how it changes the dynamic of this weak acid and base dissociation, okay? So I am gonna add, so for this one, the salt I'm gonna add is gonna be CH3COONA, okay? And then what does salt do, right? This looks all fancy, but if I give you a simple salt like NaCl, it's a table salt, right? It really dissociates into Na plus and Cl minus, right? Because it's a soluble salt. And then those ions are gonna go ahead and interact with water. That's called hydration, right? Okay, so that's what solubility means, right? This NaCl is a soluble salt, so that it dissociates into these ions, okay? So does this salt that I provide you. It's a soluble one, so it will be broken down into CH3COO minus plus Na plus. Okay, different ions. Okay, now things gonna change, okay? Because as you see, now as the salt breaks down, I have so much of this guy, right? And then this guy is also the product of my weak acid dissociation reaction. So that Le Chalais principle doesn't know that, oh, it's adding the salt that causing the product that's increasing. It just knows that there's more of my product. So Le Chalais principle is just gonna work its way and push the reaction towards the left side. Right? So in other words, I can say adding salt really caused less dissociation of my weak acid. Okay? All right. So now let's add some salt to my base. Okay? So I'm going to add NH4Cl. Okay? And then once again, this is a soluble salt. And then it's going to be broken down into NH2 plus and then Cl minus. Okay? And then you see that I have a lot of this. And this has happened to be the product of my weak acid dissociation. So that Le Chalais principle, once again, is going to push the reaction towards the right side, to the left side, right? If it goes to the right side, it will be more dissociation. It goes to the left, it's less dissociation. More reactants are reformed, okay? So this is also causing less dissociation of my weak base, okay? All right, so it's all mellow, right? It's all cool, but besides you have 2 caveats, okay? So the 2 caveats are, one is that your salt has to be soluble. Okay, so if the salt is not soluble at the first place, it's not going to break down into those ions, then the Le Chalais principle won't feel the increasement of the product, thus, towards the push the reaction towards the left, right? It has to be soluble. And then which salts are soluble, which are not, I made a video for that. You can really check my Genchem playlist. And then the second caveat is that your salt has to relate to your acid or base, in this case the weak acid or base, right? I mean, if in this case, if my salt is not NH3 COONA. If my salt is NaCl, then NaCl does dissociate. It is soluble. But the increasement of Na plus and Cl minus doesn't do anything. It has nothing to do with the products here. So Le Chalais' principle is not going to do anything, right? Okay, I hope that makes sense. That's the two caveats. Okay, so now let's reread this description from AAMC. Then you understand, okay, dissociation of weak acids and bases with or without added salt, right? So this without added salt is really just, okay, it's partially dissociating, not fully dissociating like the stronger ones, right? And then this with part is really just a fancy, confusing way to say what? Le Chalais' principle. All right, let's move on to the second topic, which is the hydrolysis of salts of weak acids and bases, okay? So this is all confusing again, right? This content, but it's okay. One step at a time. Let's just break it down, okay? Piece by piece. So my first question for you is, how is salt even made? How do you make salt from the first place, right? So for example, our famous salt, NaCl, it's an easy one. How do you produce this? So it's really NaOH plus HCl, and then this replacement reaction happens, forms NaCl plus H2O, right? That's how you create salt from the first place, right? It's the combination, the reaction of a base and an acid, okay? Okay, but the thing is, different types of acid or base, I mean, strong acid combined with a strong base can provide one type of salt, and then weak base, strong acid, different type of salt. Okay, we're going to talk about that in just a second. But before that, I need to remind you the strong acid and strong bases on periodic table. Okay, okay. So I also have a video called Ions in Solution in my Genchem playlist where you can refer to, where I talked about the strong acids and bases and also the polyatomic ions in depth. But here, just remind you really quickly. So I am going to now highlight 6 atoms for you. I mean, it's actually that, okay? These 6 atoms that I highlighted in blue, when you combine them with hydroxide, like lithium hydroxide, sodium hydroxide, so on and so forth, okay? These are all what? The strong bases, okay? SB, okay? Strong bases. All right, now I'm going to do the strong acids. I'm going to highlight 3 atoms, okay? So it's going to be Cl, Br, and I, okay? Not this fluorine. Once again, HF is a weak acid, okay? So when you combine these green highlighted atoms with a proton, with hydrogen, like a HCl, HBr, and then HI, these are strong acids, okay? And then there are other 3 strong acids that I cannot reflect on the periodic table, but just for the completion, they're H2SO4, they're HNO3, they're HClO4, okay? So these are the 6 strong acids and 6 strong bases you have to know, memorize for MCAT. You're welcome to know more, okay? All right. So with those background knowledge, okay, so let's dive into how different acids and base, depending on their strength, can create different types of salt, okay? So I have 3 cases here. The first case is really strong base, strong acid will create a neutral salt, okay? I'll explain the logic in just a bit. And then the second case is weak base, strong acid will make an acidic salt, okay? I will explain what does acidic salt mean. And then the third case is strong base, weak acid is going to produce basic salt, okay? So now let's dive into the examples and see why, okay? Okay, so the first example is the neutral salt, okay? So the neutral salt, I have LiBr here, right? And then how is LiBr made? LiBr is really LiOH and then Br, HBr, right? That gives me LiBr plus what? Plus water, right? How salt is just like NaCl. Okay, so that we know the reactant, the resources, if you will, creating this LiBr is from LiOH and HBr, right? And then how is this HBr a strong acid or weak acid? It is strong, right? It is strong acid, HBr, right? As I just told you here that I highlighted in green, okay? HBr is a strong acid. What about the lithium hydroxide, LiOH? Is that a strong base or weak base? It is a strong base, okay? So this strong base react with this strong acid, give us a neutral salt. LiBr, okay? Now let's break down what does neutral salt mean, okay? Neutral salt means when this salt, when it dissolves in water, it breaks down into La plus and then Br minus, right? And then these things really these ions really don't have any basicity or acidity that can contribute to the difference of the pH, right? It's not going to cause the pH to change, okay? Why do I say that they don't have any basicity or acidity, right? Because you may think that, okay, this is the strong base, and then LiH is the conjugate acid, right? Conjugate acid of my LiOH. Then you may think, okay, this will have some acidity? Actually, no, right? Because LiOH is a strong base. So strong bases conjugate acid is super weak, right? So the acidity of the Li plus can be neglected. It's negligible, right? We can just ignore that. We're just going to cross it out. There's no acidity, okay? Due to the strong base, LiOH, okay? And then HBr, strong acid, right? Its conjugate base, Br minus, has minimal basicity, okay? So that we can cross out this together. So the whole thing, LiBr, this salt, when you dissolve in the water, does it change the pH? No, right? It has a no effect on pH, okay? Okay, perfect. Now let's move on to our acidic salt, okay? So the acidic salt, my example is this CnNO32, okay? So the Cn, where does it from? It's from CnOH, right? What about this? This is from HNO3, okay? So that we know this guy is a strong acid, right? But this guy is really not a strong base. It's a weak base, right? As you see, Zn is not one of the atoms that I circled here for your strong base group, right? So it's a weak base. It's a weak base. And then, because it's a weak base, then it's a conjugate acid, Cn plus. It's actually what? Actually, it's 2 plus here, right? It's actually quite acidic, right? You cannot ignore the acidity of this conjugate acid, okay? So we're gonna put a check, okay? But what about this HNO3, right? HNO3, its conjugate base is really NO3 minus, right? And then this NO minus, its basicity can be ignored. We're gonna cross it. All because HNO3 is a strong acid, right? Strong acid's conjugate base is so weak, so we ignore its basicity, okay? So now all we have left is the acidity of this conjugate acid, zinc 2 plus, right? And then as this salt dissociates, it forms Cn, zinc 2 plus, and then NO3 minus, right? And then we cross out this, and then this guy, oh, we cannot ignore the acidity. So this salt is an acidic salt, okay? I hope that makes sense. Okay, and then the acidic salt really also means the salt of weak base, right? Because the reactant, one of the reactants is the weak base, right? Due to the weak base, the salt is acidic, right? So that we call it a salt of weak base, all right? So now if you go back to the title, now you read it, you can read it, you can hydrolysis of salts of weak base, okay? Salts of weak base is the acidic salt. So when this acidic salt hydrolyzes, when it breaks down into these two ions, how does that affect the pH, right? Because of the acidity that this zinc 2 plus is adding to a solution, you would really decrease your pH, okay? So now we know the effect of a hydrolysis of a salt of a weak base is that the pH decreases, okay? Now we're gonna do hydrolysis of a salt of a weak acids, okay? This is my third case. So my third case, I have a NaF, okay? And then NaF, N is from what? NaOH, right? It's a strong base, okay? So, strong base, okay? And then what about this? This is really HF, right? And then once again, HF is what? Weak acid, okay? It's weak acid. All right, so now we can tell that because it's a weak thing, right? So this weak stuff, it's a conjugate base, F minus, we cannot ignore the basicity, right? Whereas this one, the conjugate acid is Na plus, right? This acidity we can ignore. So when this salt breaks down into Na plus and then F minus, this F minus is contributing the basicity, right? So that we say, oh, this salt is a basic salt. So when this basic salt, in other words, the salt of weak acid, right? Because weak acid is the reactant that's contributing to the basicity of the salt. When this salt hydrolyzes, what does the pH do? pH will increase, right? Okay, so now let's read the title again. Now this makes a lot of sense, right? Let's read again. Hydrolysis of salts of weak acids and bases, right? Okay, perfect. All right, let's move on to the third topic. Calculation of pH of solutions of salts of weak acids and bases, okay? All right, so we are gonna first calculate the pH of the salt of weak acid, okay? All right, and then we're going to calculate the pH of the solution of salt of weak base, right? And then as we mentioned before, the salt of weak acid is just a basic salt, right? And then this is just an acidic salt, okay? So this is really the case 3 here, okay? The case 3 here. And then this is the case 2 above, right? Okay, so let's do an example, okay? So let's come up with a basic salt, okay? So I can say CH3COO okay? This salt is a basic. Why? Because that we know that this breaks down into CH3COO minus and then Na plus, right? Na plus. And then this guy is really from a weak acid, acetic acid, CH3COOH, right? It's from this weak acid. So this conjugate base, we cannot ignore the basicity of it, right? So it's a basic salt. And then because we cannot ignore the basicity of it, then we know that this thing that has basicity will just react with water like the usual weak base would do, right? Remember in our first section, first topic, we talked about the dissociation, right? So this guy, we cannot ignore the basicity so that it would react with water. It would dissociate just like the usual weak base would do, right? And then it becomes CH3 base grasped proton, COOH plus OH minus, right? Okay, so that calculate the pH is basically what? You come up with the concentration of OH. That gives you POH, right? And then you know what's pH. 14 minus POH is a pH, okay? So our goal is really to calculate the concentration of this so that we can know pH or POH, okay? Then how we do this? Then we can just say, okay, this is X molar, okay? That's the concentration of this. And then on MCAT, when the weak base really dissolves in water, when it dissociates in water, you assume that the product's concentration equal to each other, okay? So I can say, oh, this is X, then this is X as well, okay? All right, then the question might give you, okay, I have a 2 molar of my salt, okay? So that this 2 molar will dissociate into this 2 molar of this, right? But this guy here is not 2 molar, right? Because it's gonna partially dissociate. So it will be like 2 minus X. X is really like how much proton this thing grabbed, right? Okay, so now the question, also gonna tell you something like a KB, right? So to write out KB is really CH3COOH times this OH minus concentration over the reactant that is a CH3COO minus, right? And then we said these guys are both X, so X times X and then 2 minus X, that equals to KB, right? And then remember Genchem, if it's the difference is smaller than 5%, we can really ignore this, right? So we cross this out. So we have X squared equals 2 KB. And then you're going to calculate X equals whatever, right? And then this X is basically POH will equal to negative log and whatever the X is, right? And then that gives you POH. But if you want to do pH, it's really just 14 minus the POH, right? And then also, if they don't give you KB, they give you Ka, then what you do, right? You can also calculate KB, because Ka times KB equals KW, that is a 10 to the negative 14, okay? All right. So that is calculate the pH of solution of salts of weak acids. Okay, so now when you read this AAMC content list, that makes sense, right? Okay, now let's do our last calculation. Let's calculate the pH of solutions of salts of weak base. Okay, all right. So this is basically an acidic salt, right? So let's do an example. Okay, so it's a NH4Cl. That's an acidic salt, right? Because you know what, NH4 plus and then Cl minus, right? So this guy is contributing the acidity, okay? All right, so because it's contributing the acidity, so it would really just react with water like the usual weak acid would do, right? It would give up the proton. One proton becomes NH3, I mean, it's neutral now, plus H minus, right? Okay. I mean, it's H plus, okay? So yeah, acidity, right? So H plus would indicate the pH. The concentration of the H plus is just indicates a negative log pH, right? So once again, we say that if this is X and then this will be X, they're equal, okay? And then let's also say this is 2 moles of this, right? So 2 moles of this would give me 2 moles of the 2 molar of this concentration, right? And then that would give me 2 minus X, right? So I have to minus like how many protons you give up, okay? All right, so now Ka equals NH3 times H plus and then NH, the reactant 4 plus, okay? And then they're just X times X and then 2 minus X, right? 2 minus X, you can just cross that out, ignore that. So you have X squared equals 2Ka, and then you calculate your X, and then your pH is really just negative log whatever your H is, okay? All right, so it's pretty dense. I mean, now if we go back to our content list, now you can really understand what is going on, okay? Once again, disassociate of weak acids and bases with or without added salt. With is just Lascelles principle. Without is just saying partially disassociation. And the hydrolysis of salts of weak acids and salts of weak bases is really just asking if the salt is a basic salt or acidic salt, right? Because the basic salt, when it hydrolyzes, it would increase the pH, and then vice the other way for the acidic salt, okay? And then lastly is the calculation of pH. I hope that's helpful. If you found the video helpful, please subscribe, share, and like. Thank you.